For centuries, astronomers struggled to reconcile the darkness of the night with their understanding of what the universe ought to be. If you assume, as many ancient and Renaissance thinkers did, that the universe is infinite in size, eternal in age, and scattered more or less uniformly with stars, then you run into a logical catastrophe. Imagine you're standing in the center of a dense forest. If the forest is small, you can see the sky between the trunks of the trees. But if the forest stretches on forever, endless miles of timber in every direction, then eventually every line of sight from your eyes will end at the trunk of a tree. If the forest is truly infinite, there can be no gaps. The horizon would be a solid wall of wood. Now, replace the trees with stars. In an infinite, eternal universe filled with stars, every single line of sight from the earth should eventually terminate on the surface of a star. No matter where you point your telescope, no matter how tiny the patch of sky, your gaze should eventually land on a burning sun. And since surface brightness does not diminish with distance, the same way a wall looks just as bright whether you stand near it or far away, the entire night sky should be ablaze with the intensity of the solar surface. Night should not exist. The heavens should be a blinding sheet of white fire, roasting the earth and boiling away our oceans. The fact that we are not currently being vaporized and that the night sky is comfortably dark is known as Olber's paradox. Named after a 19th century German astronomer, this paradox was actually contemplated long before him. It was a problem that haunted the Newtonian view of the cosmos. Early astronomers saw the darkness as proof that the universe was finite, bounded by a wall beyond which there were no more stars. They believed we lived in an island of light, surrounded by a true empty void. But as our understanding of gravity grew, a finite universe became harder to justify physically. The paradox remained, a stubborn shadow over the Enlightenment. In the 18th century, attempts were made to solve it by suggesting that the void of space was not truly empty, but filled with a thin, interstellar fog. Thinkers reasoned that this dust and gas would absorb the light from the most distant stars, dimming them before they reached Earth, just as a morning mist dims the rising sun. It was an elegant idea, but it failed the test of thermodynamics. If the universe were truly eternal, that dust would have been absorbing starlight for infinite time. Eventually, the dust would heat up until it glowed with the same ferocity as the stars it was obscuring. The fog would become as bright as the fire. The paradox held firm. It was not a scientist, but a poet, who first stumbled upon the solution that rings closest to our modern understanding. In a prose poem titled Eureka, Edgar Allan Poe relied on intuition rather than calculation to navigate the cosmos. He suggested that the darkness of the night sky was not due to a lack of stars, but a lack of time. He proposed that the distance of the invisible background is so immense that no ray from it has yet been able to reach us at all. Poe had grasped a concept that physics would take another century to prove. The universe has a birthday. We do not live in an eternal cosmos. The universe began in a specific moment of cataclysmic expansion, the Big Bang, roughly 13.8 billion years ago. Because the speed of light is finite, traveling at approximately 300,000 kilometers per second, there is a strict horizon to what we can see. When we look out into the deep universe, we are looking back in time. We can only see the stars and galaxies whose light has had enough time to travel the vast distance to Earth. If there are stars beyond that horizon, and there almost certainly are, their light is still streaming through the void, racing toward us but not yet arrived. The forest of stars is not infinite, because the time available for us to see them is limited. We see gaps between the stars because in those directions we are looking past the galaxies and into the primordial past before the stars were born. The wall of fire that was predicted does not exist because the universe is not old enough to have filled every corner of space with light. But the finite age of the universe is only half the story. The texture of the night sky is also sculpted by the expansion of space itself. As the universe grows, the fabric of space-time stretches, carrying the galaxies apart from one another. This expansion has a profound effect on the light traveling through it. Light is a wave, and as it travels through expanding space, that wave is stretched out, like a slinky being pulled from both ends. As the wavelength lengthens, the color of the light shifts. Blue light becomes red light becomes infrared, and eventually it stretches into the long, lazy wavelengths of radio waves. This phenomenon, known as redshift, acts as a cosmic dimmer switch. The light from the most distant galaxies, the ones that might otherwise fill in the dark gaps of our sky, has been stretched so severely that it has fallen out of the visible spectrum entirely. It is no longer light that our eyes can perceive. The energy is still there, washing over the earth in a constant bath of radiation. But to our biology, it is invisible. The universe is not actually dark. It is blazing with the afterglow of creation and the light of 1 trillion distant suns, but it shines in colors we cannot see. This brings us to the final, and perhaps most intimate, reason for the blackness of the sky, the limitations of the human instrument. Our eyes are evolved for the bright sunlight of an African savanna, not the subtle whispers of deep space. The retina contains 2 types of photoreceptors: cones, which detect color and detail but require bright light to function, and rods, which are incredibly sensitive to low light but are effectively colorblind. When you step out under the stars, your eyes undergo a chemical shift. The cones shut down and the rods take over. This is scotopic vision. In this mode, the universe loses its saturation. Even if the night sky were filled with faint washes of color, the deep reds of hydrogen clouds, the teal of oxygen, the golden glow of older star clusters, your rods would report them to your brain as shades of gray. We are physiologically incapable of seeing the true colors of the faint universe. In fact, the black we see between the stars is not even true blackness. In the absence of photon stimulation, the neurons in the visual system still fire a chaotic, low-level background signal. This results in a sensation of dark gray, a color researchers call eigengrayo, or intrinsic gray. It is the color of your own optic nerve at rest. When you look at the empty spaces of the night sky, you are seeing a hallucination of darkness generated by your own biology, superimposed over a universe that is actually filled with invisible light. Even if we could see more effectively, the sky would still not be pitch black. The atmosphere of our own planet glows faintly, a phenomenon called air glow, caused by chemical reactions in the upper atmosphere powered by the sun's ultraviolet radiation. Dust in the solar system scatters sunlight, creating a faint zodiacal light that spans the ecliptic plane. And beyond our solar system, there is the cosmic optical background, the sum total of all the visible light emitted by all the stars and galaxies that have ever existed. It is a faint, diffuse glow that permeates the universe, a testament to the history of star formation. So, the blackness is an illusion. It is a product of a universe that is too young to be fully lit, an expansion that steals the energy from distant light, and an eye that is too weak to capture the faint glow that remains. The reality is that we are floating in a sea of photons. Every cubic centimeter of space is traversed by light rays from distant epochs, crisscrossing in a chaotic web of illumination. If we could perceive the full electromagnetic spectrum, the night sky would not be dark at all. It would be a chaotic, vibrant tapestry of microwave static, infrared heat, and radio hums. But we are here to discover the true color of the visible universe, the color we would see if we could step outside our galaxy, gather all the light from all the stars and galaxies, and paste it into a single beam. To do that, we must look past the illusion of the dark night. We must stop looking at the empty spaces and start looking at the sources. We have to collect the light from the local neighborhood, the distant clusters, and the ancient quasars. We have to unravel the rainbow of the cosmos. The journey to find this color began not with a camera, but with a prism. By taking the light of the universe and breaking it down into its component wavelengths, astronomers can read the chemical history of the cosmos. They can see the fingerprints of hydrogen and helium, the aging of stellar populations, and the birth of new suns. It is a process of integration, of summing up the brilliance of billions of galaxies to find a single defining hue. This quest requires us to leave the safety of our solar system and the limitations of our biological eyes. We must build instruments capable of staring into the void for weeks at a time, soaking up the scarcest photons from the edge of the observable universe. We must understand how the light of a galaxy is formed, how it changes as the galaxy ages, and how the expansion of the universe warps that light before it reaches us. The paradox of the dark night sky teaches us that what we see is only a fraction of what exists. The darkness is a canvas, but the paint is light, and that light has a color. It is not black, and it is not white. It is a specific measurable shade that tells the story of 14 billion years of cosmic evolution. To find it, we must first understand how to catch the light of a galaxy and unweave it into a spectrum, a technique that transformed astronomy from a study of motion into a study of substance. This is where the true investigation begins. To understand the true color of the universe, we must first understand the nature of light itself. To the casual observer, light is simply the means by which we see the world, a brightness that reveals the shape of a mountain or the face of a friend. But to an astrophysicist, light is something far more complex and far more talkative. It is a carrier of information, a stream of data that has traveled across the vacuum of space to deliver a message about its source. Hidden within every beam of starlight is a secret code that details the temperature, composition, age, and motion of the object that emitted it. The challenge lies in deciphering that code. The tool we use to break this cipher is the prism, or in its modern scientific incarnation, the diffraction grating. When Isaac Newton first passed a beam of sunlight through a glass prism in the 17th century, he demonstrated that white light is not a fundamental, indivisible substance. It is a composite, a choir of colors singing together in unison. The prism simply slows down the different wavelengths of light by different amounts, bending them and spreading them out into a fan of red, orange, yellow, green, blue, indigo, and violet. This fanned-out band of colors is called a spectrum. For a long time, this rainbow was seen merely as a beautiful curiosity. But in the early 19th century, a German optician named Joseph von Fraunhofer made a discovery that would transform astronomy forever. He magnified the spectrum of the sun and noticed that the rainbow was not perfect. It was interrupted by hundreds of fine, dark lines, thin shadows, where specific colors were missing. It looked as though someone had taken a fine-toothed comb and scraped away slivers of the rainbow. These dark gaps, now known as Fraunhofer lines, are the chemical fingerprints of the cosmos. They occur because atoms in the outer atmosphere of a star absorb very specific wavelengths of light. Hydrogen absorbs one set of colors, helium absorbs another. Calcium, iron, and oxygen each subtract their own unique signature from the light. By reading these lines, astronomers could do the impossible. They could touch the stars. They could determine what a celestial object was made of without ever leaving the Earth. But determining the color of the entire universe requires more than just analyzing a single star or even a single galaxy. If you wanted to know the average color of a vast autumn forest, picking up a single red maple leaf would give you a skewed answer. You would need to soar above the canopy and take in the entire vista: the red leaves, the yellowing oaks, the evergreen pines, and the brown branches, and blend them all into a single average hue. In cosmology, we cannot fly outside the universe to take such a picture. We are trapped inside the forest. To find the average color, we must perform a grand census. We must survey a volume of space large enough to be representative of the whole cosmos, capturing the light from thousands upon thousands of galaxies, and then combine them. This brings us to the red dust and eucalyptus forests of New South Wales, Australia. Here, atop a lonely ridge in the Warrumbungle National Park, sits the Siding Spring Observatory. It is a place of profound isolation where the nearest town is known as the astronomy capital of the country, and the night sky is preserved with a fierce dedication. Dominating this ridge is a massive white dome, standing like a temple to the stars. Inside lives the Anglo-Australian telescope. Commissioned in the 1970s, this telescope is a titan of the previous generation, a machine of steel and glass with a mirror nearly 4 meters across. But it was not the mirror alone that made the search for the universe's color possible. It was a revolutionary instrument attached to it, known as the 2-degree field, or simply 2DF. Before the invention of the 2-degree field system, capturing the spectrum of a galaxy was a painstakingly slow process. An astronomer would have to point the telescope at a single target, expose the camera for nearly an hour to collect enough faint light to create a spectrum, and then move the telescope to the next target. With hundreds of billions of galaxies in the universe, building a representative map one by one would have taken lifetimes. The 2-degree field changed the game. It was designed to capture the light of huge numbers of galaxies simultaneously. The instrument is a marvel of robotic engineering. It sits at the top of the telescope, at the prime focus where the starlight is concentrated. It consists of a large, circular plate drilled with holes and a robotic arm that moves with the precise, jerky grace of a mechanical insect. The process of observing with the 2-degree field is a ballet of automation. Before the night begins, astronomers select a patch of the sky containing hundreds of galaxies. The robot then goes to work. It picks up tiny optical fibers, strands of glass no thicker than a human hair, and places them onto the metal plate with magnetic buttons. Each fiber is positioned with accuracy, measured in micrometers, aligning perfectly with where the light of a specific distant galaxy will fall on the plate. The robot places up to 400 of these fibers. When the telescope points at the sky, the light from 400 different galaxies streams down the telescope tube, hits the main mirror, bounces up to the plate, and enters the 400 individual fibers. The light is then guided down the fibers like water flowing through pipes, fed into spectrographs that split each galaxy's light into its own tiny rainbow. In a single hour-long exposure, the telescope accomplishes what used to take weeks of work. In the early years of the 21st century, a team of astronomers embarked on a monumental project using this instrument. It was called the 2DF Galaxy Redshift Survey. Their primary goal was to map the three-dimensional structure of the universe, to see the vast webs and walls of galaxies that stretch across the cosmos. Over the course of several years, they collected the spectra of more than 200,000 galaxies. It was, at the time, the largest map of the universe ever constructed. But buried within this treasure trove of data was the answer to a simpler, more aesthetic question. By averaging the light from those 200,000 galaxies, the researchers could construct a single cosmic spectrum. This spectrum would represent the sum total of all the light being emitted by the stars in that massive slice of the universe. It would account for the brilliant blue giants, the steady yellow suns, and the dim red dwarfs. It would account for the dust that scatters light, and the gas that glows with the heat of newborn stars. Constructing this average spectrum was not merely a matter of addition. The astronomers had to navigate a minefield of potential errors. They had to correct for the red shift of the galaxies. Because the universe is expanding, the light from distant galaxies is stretched toward the red end of the spectrum. Before the lights could be averaged, they had to be mathematically de-shifted, brought back to the wavelength they were emitted at, so that a galaxy a billion light-years away could be fairly compared to one nearby. They also had to contend with the Earth itself. The atmosphere is a turbulent, fluid lens that distorts starlight. Even on the clearest nights at Siding Spring, the air glows with a faint luminescence. This sky glow had to be meticulously subtracted from the data, ensuring that the light being analyzed was truly from the deep cosmos and not from the oxygen atoms in the Earth's upper atmosphere. Once the data was cleaned, corrected, and combined, the result was a single, squiggly line on a graph. To the uninitiated, it might look like a random fluctuation of noise. But to an astronomer, that line is a portrait of the universe's life story. This cosmic spectrum is not a flat line. It has a distinct shape, a topography of peaks and valleys. In the ultraviolet and blue sections of the graph, the line is relatively high. This represents the energy coming from young, hot, massive stars. These stars are the rock stars of the cosmos. They live fast, burn brilliantly, and die young, often exploding as supernovae. Their light dominates the blue end of the spectrum and signifies regions where star formation is still active and vigorous. As we move toward the green and yellow parts of the graph, the line dips and then rises again. This is the domain of stars like our own sun, middle-aged, stable stars that burn for billions of years. But the most dominant feature of the cosmic spectrum appears as we move into the red and infrared. Here, the intensity of the light remains strong. This is the light of the silent majority of the universe, the countless billions of red dwarf stars and red giant stars. These are the survivors, the aging population of the cosmos. Overlaying this continuum of color are the deep gouges of the absorption lines. There is the strong, dark line of hydrogen alpha, the signature of the fuel that powers the stars. There are the complex bands of magnesium and sodium, heavy elements forged in the hearts of dying stars, and scattered into the void to become the seeds of planets. These lines tell us that the universe is chemically rich, a place that has been polluting itself with metals for billions of years. This unified spectrum is the DNA of the modern universe. It tells us that we live in a transition era. We are past the fiery blue peaks of the universe's youth, but we have not yet reached the cold, dark death of the far future. We are in the middle years, a time of settling down. The spectrum obtained by the 2DF Galaxy Redshift Survey was a triumph of statistical astronomy. It took the overwhelming complexity of the night sky, the chaotic zoo of spirals, ellipticals, irregulars, and mergers, and distilled it down to a single data set. It turned the universe into a solvable equation. However, a spectrum is still an abstraction. It is a graph of intensity versus wavelength. It is data. Humans do not see graphs, we see colors. We perceive the world through the biological filters of our eyes, mixing wavelengths to create the sensation of green or indigo or magenta. The question remained, if you took that graph, that squiggly line representing the average light of 200,000 galaxies, and fed it into the processing software of the human visual system, what color would you see? This was the question that two astronomers from the 2DF team, Carl Glazebrook and Ivan Baldry, decided to answer in roughly 2002. It started almost as a whimsical side project, a way to make the dry data of the survey accessible to the public. They wanted to visualize the data. They wanted to know what the universe would look like if it were compressed into a single, glowing marble. The process of converting a spectrum into a visible color is a science in itself, known as colorimetry. It involves mapping the physical wavelengths of light to the sensitivity curves of the three cones in the human eye, the long, medium, and short wavelength receptors that we loosely call red, green, and blue. The eye is not a perfect spectrometer. It is a biased instrument. It is incredibly sensitive to green light, less so to red and blue. The exact perception of color depends on the light source, the observer, and even the background against which the color is viewed. Glazebrook and Baldry had to calculate how the cosmic spectrum would stimulate a standard human observer's eye under standard lighting conditions. They ran the numbers. They took the combined light of the 200,000 galaxies, integrated it over the visible spectrum, weighted it by the human eye's response, and waited for the computer to spit out a hexadecimal code or an RGB value that represented the color of the cosmos. The result that appeared on their screens would spark a minor media frenzy and lead to one of the most amusing corrections in the history of science. The color they initially found was not what anyone expected. It wasn't black, and it wasn't white. According to their first calculation, the universe was a distinct, rather pleasant shade of pale turquoise. It seemed that the universe was teal. This finding made headlines around the world. It was a beautiful, evocative image. We live in a turquoise universe. It felt fresh, almost aquatic. But as we will see, science is rarely a straight path to the truth. There was a ghost in the machine, a subtle flaw in the software that had shifted the result. The turquoise universe was an illusion, a phantom color born of a coding error. But before the correction could be made, before the true color could be revealed, the idea of the turquoise cosmos had already taken root. It served as a reminder of how difficult it is to translate the raw, physical reality of the universe into the limited language of human perception. We are trying to force the infinite variety of galactic light into the narrow bandwidth of our primate evolution, The unweaving of the galactic rainbow at the Anglo-Australian telescope was a masterpiece of observation. It gave us the raw materials to paint the portrait of the universe. It showed us that the light of the cosmos is a mixture of the fierce blue of youth and the steady red of age. It proved that we can understand the universe as a whole, rather than just as a collection of disjointed parts. The fibers of the 2-degree field instrument, clicking into place night after night on that Australian ridge, were like the needles of a knitting machine, pulling together the threads of the cosmos. They captured the light that had been traveling for millions or billions of years, light that carried the memory of the stars that created it. And although the first attempt to interpret that light led us down a turquoise garden path, the data itself was sound. The spectrum was correct. The recipe for the color of the universe was sitting there, waiting for the right pair of eyes to read it. As we move forward to understand the true shade of the modern cosmos, we must appreciate the delicacy of this work. We are dealing with the average of averages, a statistical game played on a canvas of billions of light years. The fact that we can assign a color to the universe at all is a testament to the power of human curiosity and the precision of our machines. We have reached out, caught the ghost of the universe's light, and held it still long enough to ask, "What color are you?" The answer, as it turns out, is much closer to home than a shade of exotic turquoise. It is a color that reflects the comfort and stability of our current epoch. But arriving at that answer required a public retraction, a re-evaluation of the white point, and a journey into the world of beige. The year was 2002, and for a brief, shimmering moment, humanity believed it lived in a turquoise universe. The news broke during a meeting of the American Astronomical Society, a gathering that is usually a sedate affair of PowerPoint presentations and coffee breaks. But when Carl Glazebrook and Ivan Baldry presented their initial findings from the 2DF Galaxy Redshift Survey, the story leaped from the academic journals to the front pages of newspapers worldwide. The idea was captivating. The scientists had taken the average light of the cosmos and determined that it was a distinct medium teal. It was a color that suggested tropical oceans, oxidized copper, or the eggs of a robin. It felt exotic and vibrant, a hue befitting a universe filled with nebulae and quasars. People loved it. It was a color you could paint a nursery. It was a color that felt alive. It seemed to confirm that the cosmos was a place of mystery and alien beauty. But science is a self-correcting discipline, and sometimes the correction comes from an unlikely source. As the turquoise news circulated, it caught the eye of color scientists at the Munsell Color Science Laboratory in Rochester, New York. These were not astrophysicists. They were experts in the perception of color, the people who understand the physics of pigments and the psychophysics of the human eye. Mark Fairchild, a scientist at the lab, looked at the results and noticed something suspicious. The shade of turquoise reported was too saturated, too specific. It didn't seem to align with the known distribution of stellar temperatures. Fairchild reached out to the astronomers with a polite but probing question. "What white point did you use?" To understand the magnitude of this question, we have to delve into the subtle subjectivity of color. There is no such thing as white in an absolute sense. A sheet of paper looks white under the yellow glow of a candle, the harsh blue of a fluorescent tube, or the neutral light of the midday sun. Our brains are incredibly good at white balancing, automatically adjusting our perception so that white objects appear white regardless of the lighting. But computers and cameras are not so intuitive. They need a reference point. they need to be told what white is mathematically defined as. When the astronomers ran their original software to convert the cosmic spectrum into a visible color, the program used a default setting. It assumed a white point that was not standard for human vision under natural lighting. In essence, the software was looking at the universe through blue-tinted sunglasses. It had artificially boosted the blue end of the spectrum, shifting the result from a neutral tone into that lovely but erroneous turquoise. Glazebrook and Baldry returned to their calculations. They stripped away the software's default bias and applied the standard CERA reference illuminant, which mimics the response of the human eye under daylight conditions. They fed the spectrum back into the equations, carefully balancing the photon energies against the sensitivity curves of the human retina. The turquoise melted away. The blue saturation vanished. What remained on the screen was something far more humble. The true color of the universe, the average hue of all the light emitted by all the stars and galaxies at this moment in cosmic history, was a soft, pale, creamy white. It was the color of heavy cream, of old parchment, of a vanilla milkshake, or perhaps the limestone of an ancient building. It was, to be blunt, beige. The correction was published, and the media cycle churned once again. "Universe is beige" is a headline that lands with a very different impact than "Universe is turquoise." It sounds less like a sci-fi epic and more like an interior design catalog. There was a sense of comedic deflation. We inhabit a cosmos that matches the color of a sensible pair of khakis or the walls of a rental apartment. But to dismiss this color as boring is to miss the profound reality it represents. This specific shade of beige is the visual signature of the universe's maturity. It is the result of a delicate cosmic equilibrium. If the universe were younger, dominated by the fierce, blue-white heat of massive, short-lived stars, the average color would indeed be blue. If the universe were infinitely old, filled only with the dying embers of red dwarfs and cooling white dwarfs, the color would be a deep, ruddy crimson. We live in the Goldilocks era of cosmic time. The massive blue stars are still being born, injecting energy and brightness into the mix, but their numbers are dwindling. Meanwhile, the population of older, redder stars has built up over billions of years, pulling the average toward the warm end of the spectrum. The beige color is the balance point between the vigor of youth and the lethargy of age. It is the color of a galaxy that is settled, stable, and chemically complex. Recognizing the need to rebrand this somewhat lackluster discovery, the astronomers decided to embrace the fun of the situation. They realized that cosmic beige was not a name that would inspire wonder. So, they did what any good scientist does when faced with a marketing problem. They crowd-sourced it. They accepted suggestions from the public to name the new color. The entries poured in. Some were whimsical, some were poetic, and some were delightfully cynical. Cappuccino Cosmico was a strong contender, playing on the frothy, coffee-stained white of the hue. Big Bang Beige had a nice alliterative ring to it, though it was technically inaccurate since the color applies to the now, not the Big Bang. Skyvory, a portmanteau of sky and ivory, was elegant but perhaps too artistic. Unibeige was proposed, but it sounded too much like a cleaning product. The winner, suggested by Peter Drum and several others, was Cosmic Latte. The name was perfect. Latte implies a milky appearance, connecting deeply to the name of our own galaxy, the Milky Way, or Via Lactea. It suggests a mixture, a blending of the strong, dark espresso of the void with the frothy light foam of the stars. It captures the essence of the color, a white that isn't stark or sterile but warm, comforting, and organic. So, officially, the color of the universe is cosmic latte. If you want to visualize this color accurately, imagine looking at a white piece of paper in the late afternoon, when the sun is beginning to dip toward the horizon and the light takes on a golden, buttery quality. It is extremely close to pure white. In fact, if you were placed in a room painted entirely in cosmic latte, with no other colors for comparison, your brain would almost certainly interpret it as white. It is only when placed directly next to a standard pure white reference that the subtle warmth becomes visible. It has a slight reddish-yellow undertone, a faint blush that speaks to the dominance of red giant stars in the current stellar population. To define it with the precision of digital design, the color has specific RGB values. In the hexadecimal code used by web designers, it is roughly FFF8E7. It is a very bright color. This is an important distinction. The darkness of space is a result of the sparsity of light sources, but the color of the light itself is bright. If you could gather all the photons of the universe and compress them into a ball, that ball would not be dim. It would glow with a luminous, pale intensity. This realization forces us to rethink our mental image of the universe. We tend to think of space as a cold, blue-black ocean, but the stuff of the universe, the stars and galaxies that make up its physical reality, is actually glowing with the warmth of an incandescent light bulb. The universe is not a fluorescent office building. It is a candle-lit library. The discovery of cosmic latte also highlights the importance of the chromaticity diagram, a tool used by color scientists to map the landscape of human vision. This diagram usually takes the shape of a horseshoe, containing all the colors the human eye can see. The curved edge represents pure, single wavelength colors, the deep spectral reds, greens, and blues. The interior represents the mixtures, the pastels and muds and washes of the world. Cosmic latte sits very close to the center of this diagram, near what is known as the Planckian locus. This is a curved line that traces the color of a black body radiator as it heats up. A black body is an idealized physical object that glows purely because of its temperature. An iron poker in a fire is a rough approximation. It glows dull red, then orange, then yellow, then white, and finally blue-white as it gets hotter. The universe behaves remarkably like a black body radiator. Because stars are essentially hot balls of gas, their combined light follows this same physical law. The temperature that corresponds to cosmic latte is roughly 5,800 Kelvin. This is uncannily close to the surface temperature of our own sun. This is a beautiful coincidence. The light of the entire universe, averaged over hundreds of thousands of galaxies and billions of light years, turns out to be almost exactly the same color as the light from our home star. When you look at the sun, safely of course, or see its light reflecting off a cloud, you are seeing a local sample of the universal average. The daylight that fuels the photosynthesis of plants and warms the surface of the earth is a microcosm of the light that fills the entire cosmos. We are not outliers living under a strange, exotic star. We are bathed in the common light of the universe. However, cosmic latte is not a static paint chip. It is a snapshot. It represents the color of the universe right now, at redshift 0. If we were to perform this same experiment 1 billion years in the past, or 1 billion years in the future, the answer would be different. The color of the universe is a function of time. It is a changing variable in the equation of cosmic evolution. In the grand scheme of things, the beiging of the universe is a relatively recent phenomenon. For the first few billion years of its existence, the universe was a very different place, painted in shades that would appear alien to our modern eyes. The story of how we arrived at cosmic Latte is a story of aging. It is the story of a universe that has transitioned from a frenzy of creation to a steady state of existence. To understand the significance of this creamy white hue, we must look backward. We must rewind the clock to a time before the red giants took over, to a time when the universe was bursting with raw elemental power. We must look to the era of the blue youth, when the cosmos was not a place of beige comfort, but a forge of blinding azure intensity. The pale shade of cosmic Latte is effectively the gray hair of the universe. It signifies that the rate of new star birth is declining. The great star-forming factories are running out of raw gas. The massive, brilliant blue stars that defined the early epochs have largely died out, exploding as supernovae and vanishing into black holes. What is left are the thrifty survivors, the stars that sip their fuel slowly and glow with a lower, redder heat. This transition is captured perfectly in the spectrum that Glazebrook and Baldry analyzed. The strong peaks in the red and infrared are the statistical weight of these billions of aging stars. The faintness of the blue end of the spectrum is a testament to the rarity of new massive stars. The universe is settling down. It is entering its afternoon. The quest for the color of the universe, therefore, became a lesson in humility. We wanted something spectacular. We wanted turquoise. We wanted a color that screamed sci-fi. Instead, the universe gave us the color of a latte. It gave us a color that implies warmth, domesticity, and stability. It is a color that tells us we are living in a universe that has matured enough to support life, a universe that has moved past the violent, sterilizing radiation of its youth and settled into a long, steady burn. As we prepared to look deeper into the past, to trace the lineage of this color, we realize that cosmic Latte is not just a novelty. It is a thermometer. It is a clock. By measuring the precise shade of this beige, astronomers can determine exactly where we stand in the life cycle of the cosmos. A slightly bluer beige would mean we were closer to the peak of star formation. A slightly redder beige would mean we were further along the path to heat death. Cosmic Latte is the color of the present moment. It is the flag of the Holocene, the banner of the era of humanity. But to fully appreciate it, we must contrast it with what came before. We must peel back the layers of time and look at the universe as it was when it was young, wild, and brilliantly, blindingly blue. This historical perspective reveals that the universe is not just a place, but a process that is slowly, inexorably changing its palette from the hot end of the spectrum to the cold. If cosmic Latte is the color of the present, a creamy, beige testament to a universe that has settled into a comfortable maturity, then it stands to reason that the universe was not always this shade. Color, in the astronomical sense, is a measure of time. It is a shifting variable that tracks the life cycle of the cosmos, just as graying hair tracks the life cycle of a human being. If we were to take the film reel of the universe and wind it back billions of years, playing it in reverse, the beige would drain away. The soft, buttery warmth of the modern sky would be replaced by a stark, piercing intensity. The color of the cosmos would shift from the hue of old parchment to the brilliant electric blue of a welding arc. To understand this chronological shift, we must understand the changing demographics of the stellar population. The color of the universe is determined by which stars are shouting the loudest. In our current era, the loud blue giants are rare, and the quiet red dwarfs are numerous, creating that balanced beige. But in the deep past, the balance of power was different. The universe was a frantic industrial landscape of star production, a time when the galaxies were lighting up like neon signs. Astronomers call this era cosmic high noon. It occurred roughly 10 to 11 billion years ago, when the universe was only a few billion years old. During this period, the rate of star formation was not just higher than it is today, it was frantic. The galaxies were rich with cold, dense hydrogen gas, the raw fuel required to build stars. Gravity was pulling this gas together in vast, collapsing clouds, igniting nuclear fusion on a scale that is difficult to comprehend from our quiet vantage point in the 21st century. In this era, the universe was dominated by the most massive class of stars, the O-type and B-type supergiants. These are the titans of the stellar family. A single O-type star can be tens of thousands of times more luminous than our Sun. They burn with such ferocity that their surface temperatures soar to 30,000 or 40,000 degrees. At these temperatures, a star does not glow yellow or white. It glows with a fierce, saturated blue, pouring out immense amounts of ultraviolet radiation. Although these blue giants are rare in terms of pure numbers, even back then they were outnumbered by smaller stars. They are so incredibly bright that they bully the average. Imagine a stadium filled with thousands of people holding dim red candles and 10 people holding blindingly bright blue magnesium flares. If you squinted and looked at the stadium from a mile away, you wouldn't see the red candles. You would see a glowing blue ball of light. The flares drown out the candles. This was the state of the universe 10 billion years ago. It was a blue universe. If we could transport our eyes back to that epoch, floating in the space between the young, jagged galaxies, we would see a cosmos that looked nothing like a latte. It would look like the heart of a flame. The average color would have been a pale turquoise, very similar to the erroneous color originally reported by the astronomers in 2002. In a twist of cosmic irony, the software glitch that briefly misled the world had accidentally predicted the color of the universe's youth. This turquoise period was the universe's adolescence. It was a time of violence and growth. Galaxies were crashing into one another, merging and triggering massive bursts of star formation. The gas was turbulent. Black holes in the centers of these galaxies were gorging on the infalling material, blazing as quasars that outshone their entire host galaxies. It was a time of maximum energy, painted in the cool, hard hues of the upper spectrum. But this blue dominance came with a built-in expiration date. The physics of stars is governed by a cruel rule. The more massive you are, the shorter your life. A small red dwarf star can sip its hydrogen fuel for trillions of years, glowing dimly but consistently, essentially forever. A massive blue supergiant, however, guzzles its fuel with reckless abandon. It burns through its vast reserves of hydrogen in only a few million years, a cosmic blink of an eye. Because of this, the blue color of the universe is fragile. It requires constant replenishment. To keep the universe blue, you need to keep making new blue stars to replace the ones that are dying. As long as the galaxies had plenty of gas, this cycle continued. The old blue giants exploded as supernovae. scattering heavy metals into the void, and new blue giants were born from the remaining gas clouds to take their place. The turquoise glow was sustained by a constant turnover of the stellar population. But the gas could not last forever. Over billions of years, the frenetic pace of cosmic high noon began to drain the reservoirs of the universe. Much of the gas was locked away inside long-lived stars like our Sun, or trapped in the dead remnants of white dwarfs and neutron stars. Some of it was blown out of galaxies entirely by the powerful winds of the supermassive black holes, exiled into the deep intergalactic voids, where it became too thin and too hot to ever collapse into stars again. As the fuel supply dwindled, the birth rate of new stars began to plummet. The production of the massive blue giants slowed down, and this is where the color shift began. When you stop making blue stars, the color of your galaxy starts to drift. The existing blue stars die out quickly, disappearing from the chorus. But the yellow stars, the orange stars, and the red stars keep burning. They are the survivors. Slowly, inexorably, the blue tint faded. The turquoise washed out, replaced first by a neutral white, and then, as the billions of years ticked by, the creamy beige we see today. We are living in the aftermath of the party. The great blue bonfires of the early universe have largely burned down to embers, and we are left with the steady, glowing coals of the medium-mass stars. This transition from blue to beige is not just a story of individual stars, it is a story of galactic evolution. Astronomers classify galaxies into two broad color categories, the blue cloud and the red sequence. The blue cloud is made up of spiral galaxies like the Milky Way that are still actively forming stars. They have gas, they have dust, they have the ingredients to make new blue giants. The red sequence is made up of elliptical galaxies, massive blob-like swarms of stars that have used up all their gas. They are red and dead. They have no new star formation, only a population of aging, reddish stars orbiting in a swarm. For the last 7 or 8 billion years, the traffic has been moving in one direction, from the blue cloud to the red sequence. Galaxies run out of gas, or they merge and scramble their structures, shutting down their star factories. As more and more galaxies cross this line, the average color of the entire universe slides further toward the red. Tracing this timeline requires us to be careful about how we use the word color. When we look at distant galaxies with our telescopes today, we do not see them as blue. We see them as deep, deep red. But this is an illusion caused by the expansion of space. The phenomenon of redshift we touched upon earlier. The light from those young blue stars has been stretched by the expansion of the universe as it traveled toward us. A photon that started its journey as a piercing ray of ultraviolet light 10 billion years ago might arrive at the Hubble Space Telescope today as a weary wave of infrared. To reconstruct the true history of cosmic color, astronomers must mathematically reverse this expansion. They have to correct for the redshift, shrinking the wavelengths back to their original size to see the light as it was when it was emitted. When they do this, when they strip away the effects of travel time and expansion, the K-correction reveals the truth. The distant red smudges in our telescope images were actually blazing blue beacons. We can chart this evolution on a graph, a curve that slopes downward from the blue peaks of the past to the beige valley of the present. This curve is known as the cosmic spectrum evolution. It shows that the universe has been darkening and reddening for most of its history. The brightness of the universe, the amount of light produced per cubic light year, peaked during that high noon era and has been falling ever since. We are living in a universe that is significantly dimmer and redder than it was at its peak. But the story of the blue youth and the red age is also a story of chemical complexity. The early blue universe was chemically simple. It was made almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. The first generations of stars were pure, metal-free spheres of gas. The light they emitted was raw and harsh. As those stars died, they forged the heavier elements, carbon, oxygen, nitrogen, iron, in their cores and exploded them into space. The beige universe of today is a dirty universe. It is polluted with the ashes of dead stars. The dust clouds that drift through the Milky Way, blocking the light of the center, are made of these heavy elements. This dust has a further reddening effect. Just as a sunset looks red because the atmosphere scatters the blue light away, the dust in galaxies scatters the blue starlight, allowing the red wavelengths to pass through more easily. So, the modern universe is redder not only because the stars are cooler, but because the galaxies are dustier. This chronological journey clarifies our place in history. We occupy a sweet spot. We are late enough in the universe's life that the heavy elements exist. Without the carbon and oxygen forged by those early blue stars, Earth and humanity could not exist. We are made of the debris of the turquoise era, but we are early enough that the universe is still illuminated. There are still enough new stars being born to keep the galaxy shining with a white-hot intensity, even if it is softer than before. If we look toward the future, the trend is obvious. The beige will deepen. As the sun-like stars eventually die and fade into white dwarfs, they will leave the stage to the true immortals of the cosmos, the red dwarfs. These tiny stars, with masses only a fraction of the sun's, burn so slowly that they will outlast the current age of the universe by trillions of years. In the far, far future, they will be the only things left shining. The cosmic latte will curdle into a cosmic mocha, and eventually into a deep, dim maroon. But before we resign ourselves to the fading light of the future, we must acknowledge that the blue youth was not the beginning. Before the turquoise era of the first stars, there was a time when the universe had no stars at all. There was a time when the color of the cosmos was not determined by fusion reactors, but by the cooling glow of the Big Bang itself. To find the true, original color of the universe, the primordial fire, we have to look back even further, past the galaxies, past the first stars, to a wall of light that marks the limit of our vision. This was the moment when the universe first became transparent, when the fog of creation lifted and light was set free to travel the cosmos. What did that first light look like? Was it white? Was it blue? Or was it something else entirely? To answer this, we must travel back to a time when the entire universe was a single, glowing star. A time when space itself was an inferno of orange and red that would eventually fade into the invisible static that fills the space between the stars today. This is the era of the cosmic microwave background, the afterglow that sets the baseline for all colors that would follow. To find the true, original color of the universe, we must abandon the realm of stars entirely. We must travel back before the dominance of the red giants, back before the frantic brilliance of the blue supergiants, and even before the very first galaxy began to spiral in the dark. We have to rewind the cosmic tape to a time when the universe was not a collection of isolated islands of light floating in a black void, but a single, continuous ocean of energy. If you were to stand in the universe at this moment, roughly 380,000 years after the Big Bang, you would not see a night sky. You would not see darkness or points of light, or the familiar contrast of shadow and illumination. You would be immersed in a fog of blinding, uniform brightness. There would be no up and no down, no sun and no moon. Every direction you looked would be filled with the same wall of glowing intensity. For the first few 100,000 years of its existence, the universe was a trap for light. It was incredibly hot and incredibly dense, so dense that atoms as we know them could not exist. The cosmos was filled with a plasma, a soup of protons and electrons that were too energetic to settle down and form hydrogen. In this state, the universe was opaque. It was like the interior of a cloud, or the inside of a fluorescent tube. A photon of light, born in the heat of this plasma, could not travel far. It would move a tiny fraction of an inch before crashing into a free electron, bouncing off in a random direction, then crashing into another and another. Light was a prisoner, locked in a pinball game of subatomic chaos. The universe was brilliant, but it was a trapped brilliance, a light that could not shine because it had nowhere to go. It was a fog of fire, but the universe was expanding. As space stretched, the plasma cooled. The frenetic energy of the particles began to slow down. The temperature dropped from billions of degrees down to millions, and finally it reached a critical threshold of around 3,000 degrees Kelvin. This was the moment of recombination. It is one of the most profound turning points in the history of existence. At this temperature, the electrons slowed down just enough that the protons could snag them, pulling them into orbit. For the first time, stable neutral atoms of hydrogen were formed. The fog of free electrons vanished. Suddenly, the pathways were open. The photons, which had been bouncing aimlessly for millennia, found themselves traveling through empty space. The universe, in a single cosmic instant, became transparent. The light that was released at that moment is the oldest light in the universe. It is the afterglow of the Big Bang itself, and unlike the light of a star, which comes from a single point, this light came from everywhere. It was the glow of the universe's own body. So, what color was it? If you had been there to witness this great unveiling, the breaking of the cosmic fog, you would have been bathed in a light that corresponds to the temperature of that cooling gas. 3,000 Kelvin is a temperature familiar to us on Earth. It is roughly the temperature of the tungsten filament in an old-fashioned 60-watt light bulb. It is the temperature of a dying ember in a campfire or the surface of a red dwarf star. The color of the infant universe was a warm, bright, pale orange. It was not the angry, violet-white heat of the earlier epochs, nor was it the deep, cool red of the far future. It was a soft, tangerine glow, leaning toward a yellowish white. Imagine a sky that is not blue, but completely filled with the color of a peach or a cantaloupe, glowing with the intensity of 1,000 suns. It would have been a breathtaking, oppressive beauty, a dome of pure, shadowless orange light stretching to infinity in every direction. This cosmic orange was the baseline color of reality. It was the canvas upon which everything else would eventually be painted. But this moment of orange perfection was fleeting. The universe did not stay 3,000 degrees for long. The expansion of space continued, relentless and indifferent, and as it stretched the fabric of the cosmos, it stretched the light waves themselves. We have spoken of redshift as a tool for measuring the speed of receding galaxies, But in the early universe, redshift was the engine of a great darkening. As the wavelengths of that pale orange light were pulled apart by the expansion, they shifted toward the red. The universe transitioned from the bright, hot orange of a light bulb to the deep, bloody crimson of a dying fire. The light grew dimmer and redder with every passing million years. Eventually, the wavelengths were stretched so far that they crossed the boundary of human vision. The crimson faded into the infrared. The heat remained, but the light vanished. To human eyes, the universe went pitch black. This marked the beginning of the era known as the Cosmic Dark Ages. It was a time of profound silence. The primordial fire had faded into invisibility, but the first stars had not yet ignited to replace it. For hundreds of millions of years, the universe was truly, completely dark. It was a vast sea of invisible infrared radiation and neutral hydrogen gas, waiting for gravity to curdle the darkness into the first points of light. But that original orange light did not disappear. Energy cannot be destroyed. It can only be changed. The light continued to travel through the void, passing through the forming galaxies, passing through the dust and the gas, always moving, always being stretched. It became a ghost, haunting the universe with the memory of its fiery birth. As the eons passed, the expansion of the universe accelerated, pulling the wavelengths of this ancient light even further. It was stretched from infrared into the realm of microwaves, waves that are millimeters or centimeters long. These are the same kind of waves that cook our food or carry our Wi-Fi signals. The blazing orange fire of the Big Bang had cooled and expanded until it became a cold, low-energy hum. For billions of years, this microwave background radiation washed over the Earth, unnoticed. It rained down on the dinosaurs. It passed through the stone cathedrals of the Middle Ages. It vibrated the antennas of the first radios. It was everywhere, a constant static hiss filling the sky. But we lacked the ears to hear it and the eyes to see it. The discovery of this invisible afterglow is one of the great accidental triumphs of science. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in Holmdel, New Jersey. They were not looking for the origin of the universe. They were trying to calibrate a massive, horn-shaped antenna designed to communicate with the first generation of satellites. They had a problem. No matter where they pointed their antenna, whether at the Milky Way, or at the empty spaces between the stars, or even at the ground, they picked up a persistent, low-level noise. It was a steady, annoying hiss that wouldn't go away. They assumed it was a defect in their equipment. They checked the wiring. They taped over the rivets in the metal dish to ensure smooth flow for the radio waves. They even climbed into the horn with brooms and scrub brushes to clean out the droppings of pigeons that had been roosting inside, famously referring to the guano as white dielectric material. But after cleaning the antenna, evicting the pigeons, and ruling out interference from nearby New York City, the hiss remained. It was constant, day and night, summer and winter. It came from every direction in the sky, with perfect uniformity. At the same time, just a few miles away at Princeton University, a team of theoretical physicists led by Robert Dicke was predicting that if the Big Bang had happened, there should be a leftover radiation field. They calculated that the heat of the early universe should have cooled down by now to just a few degrees above absolute zero, manifesting as microwave radiation. They were preparing to build a telescope to look for it. When Penzias and Wilson mentioned their unsolvable noise problem to the Princeton researchers, The pieces clicked into place. The annoying static wasn't pigeon droppings, and it wasn't a loose wire. It was the sound of the universe being born. It was the red-shifted, stretched-out, cooled-down remnant of that original cosmic orange light. This radiation is now known as the cosmic microwave background, or CMB. It is the single strongest piece of evidence we have for the Big Bang. When we look at the sky with microwave eyes, the darkness vanishes. The universe is ablaze. The CMB fills 99.9% of the photons in the universe. If your eyes could see microwaves, the night sky would not be black at all. It would be a glowing wall of uniform brightness, exactly as it was 380,000 years after the Big Bang. Only now the color has shifted far beyond the rainbow we can see. In a very real sense, the sky is still orange. We are just moving away from the source so fast that the orange looks like static. The temperature of this radiation today is 2.725 Kelvin, just a hair's breadth above absolute zero. It is incredibly cold. The fire has become an icebox. But the uniformity of this temperature is what confirms our origin story. The fact that the radiation is the same intensity in every direction tells us that the universe was once a single, connected, hot fluid. Detailed maps of the CMB, created by satellites like COBE, WMAP, and Planck, show tiny fluctuations in this temperature, variations of just a few hundred thousandths of a degree. These tiny ripples in the orange wall are the seeds of everything we see today. They represent slightly denser regions in the primordial plasma, where gravity would eventually pull matter together to form the first stars and galaxies. Without those tiny imperfections in the smooth orange glow, the universe would have remained a featureless soup forever. The journey of this light tells us that the true color of the universe depends entirely on when you look at it. There was the primordial orange of the beginning. There was the invisible black of the Dark Ages. There was the blazing turquoise of the first starbursts, and there is the creamy beige of the modern era. But this journey is not over. The stretching continues. The universe is not static. It is expanding, and that expansion is accelerating. The cosmic microwave background, which started as visible light, will eventually be stretched into radio waves with wavelengths kilometers long. The energy of the universe is being diluted, spread thinner and thinner across an ever-widening void. This leads us to a sobering realization. We live in a privileged time. We are capable of seeing the stars because the universe is transparent. We are capable of seeing the cosmic microwave background because our technology can detect those wavelengths. But the forces that turn the orange fire into invisible microwaves are still at work. They are dragging the universe toward a future where light itself becomes a scarce commodity. The beige of the cosmic latte is a temporary state. It is a plateau in a long decline. Just as the orange faded to black, and the black ignited into blue, and the blue settled into beige, the beige will eventually give way. The stars are fuel tanks, and their gauges are dropping. The universe is slowly running out of the capacity to create visible light. We have traced the color of the cosmos from the incandescent fireball of its birth to the comfortable, sun-like warmth of today. But what happens next? What is the final color of the universe? To answer that, we must project our timeline forward, past the death of the sun, past the collision of the Milky Way and Andromeda, and into the deep, deep time of the stellar graveyard. The future of the universe is not just a fading of the light, it is a shift in the very nature of the radiation that fills the void. The beige will darken, the red will deepen, and eventually the universe will return to the state it knew in the Dark Ages, a place of silence, where the only light that remains is too faint and too long-waved for any eye to see. The story of the universe's color is ultimately a story of fading. It is a slow dissolve to black. But before the final darkness, there will be a long twilight era, an era of red dwarfs and white dwarfs, a time when the universe will glow with a dim, ruddy luminescence that will last for trillions of years. This is the era of the Red Age, the final chapter of visible light. We have traced the chromatic history of our universe from the blinding, uniform orange of the Big Bang's afterglow, through the invisible silence of the Dark Ages, into the brilliant turquoise frenzy of the first stars, and finally to the calm, creamy beige of the present day. But a story is defined by its ending, and the story of light is no exception. The cosmic latte that currently paints the average canvas of the night sky is not a permanent fixture. It is merely a snapshot of a universe in its middle age, a universe that is slowly, inexorably winding down. To understand the true color of the cosmos, we must look beyond the present, into the deep, vertiginous expanse of the future, where the lights begin to go out one by one. The transition from our current era to the next will not be sudden. The universe operates on timescales that mock human comprehension. The shift will be a slow, agonizing fade, a gradual dimming of the great galactic chandeliers. As we look forward, the first thing we must accept is that the era of star formation, the engine that replenishes the blue and white light of the cosmos, is effectively over. We have passed the peak. The universe produced the vast majority of its stars billions of years ago. Today we are living on the reserves. In the near future, which in cosmological terms means the next 4 or 5 billion years, our own corner of the universe will provide a spectacular example of this aging process. The Milky Way is currently on a collision course with our nearest large neighbor, the Andromeda Galaxy. To a human observer on Earth, this slow-motion crash will initially spark a brief renaissance of color. As the great spiral arms interact, compressing gas clouds, there will be a burst of new star formation. The sky will light up with a fresh generation of blue stars, a temporary flash of the turquoise youth we left behind long ago. But this will be a last hurrah, a final firework display before the silence settles in. Once the two galaxies merge, the chaotic gas clouds will be used up or blown away. The beautiful spiral structures, which are the factories of new stars, will be destroyed. The resulting object will be a giant elliptical galaxy, often nicknamed Milkomeda. It will be a vast, amorphous blob of stars, devoid of the structure needed to create new suns. The blue stars will die out, exploding and fading away, leaving only the older, redder population. The color of our local universe will shift from the mixed white of the Milky Way to the deep, rusty orange of a retirement home for stars. This process will be repeated across the entire cosmos. As the supply of hydrogen gas is exhausted, the blue stars, the O and B types that give the universe its vigor, will vanish from the sky. They are the spendthrifts of the galaxy, burning their fuel in a few million years. Once they are gone forever. The universe will be left with the thrifty survivors, the yellow G-type stars, like our Sun, and the orange K-type stars. But even these are mortal. In 5 billion years, our Sun will swell into a red giant, casting off its outer layers and collapsing into a white dwarf. In 10 billion years, most of the sun-like stars will have followed suit. The cosmic latte, that comforting beige, will darken. The cream will disappear from the coffee. The universe will enter the era of the red dwarfs. Red dwarfs, or M dwarfs, are the cockroaches of the stellar world. They are small, dim, and incredibly numerous, making up roughly 70% of all stars in the universe. But their defining characteristic is their longevity. Because they are small, they burn their hydrogen fuel at a microscopic rate. A star like Proxima Centauri will continue to shine for trillions of years, thousands of times longer than the current age of the universe. For eons, these red dwarfs will be the only things illuminating the void. If you were to transport the 2-degree field instrument to a planet in this distant era, trillions of years from now, and attempt to measure the average color of the universe, the result would be radically different. The spectrum would be heavily weighted toward the infrared. To the human eye, the visible color of the cosmos would be a deep, dull maroon. It would look like the embers of a dying fire, a sullen, glowing coal suspended in the dark. The brightness would be a tiny fraction of what we see today. The sky would be almost black, punctuated only by the faint, ruddy glow of these ancient, miserly stars. This red age will be the longest period in the history of stellar illumination. It will stretch on for so long that the 14 billion years of the blue and beige eras will seem like a momentary flash in the pan, a brief spark at the very beginning of time. But thermodynamics is patient, and it is cruel. Even the red dwarfs have a limited supply of fuel. One by one, over trillions of years, the red dwarfs will exhaust their hydrogen. Unlike the massive stars that go out with a supernova bang, red dwarfs die with a whimper. They simply fade. They shrink and heat up slightly as they collapse, briefly becoming blue dwarfs, a theoretical phase we have never seen because the universe is not yet old enough for any red dwarf to have died before settling down as white dwarfs. There will come a day in the unimaginably distant future when the very last star in the universe is born. It will likely be a small, scrappy thing, coalescing from the last dregs of hydrogen gas in a dark and lonely galaxy. It will shine for its allotted span, a solitary beacon in a universe that has largely gone dark. And then, it too will run out of fuel. When that last star flickers and dies, the stelliferous era, the age of stars, will come to a close. The universe will no longer be painted with the light of nuclear fusion. The concept of color as we understand it, which relies on the emission of visible light from hot plasma, will become a relic of the ancient past. What will remain? The universe will be populated by the corpses of stars. There will be white dwarfs, neutron stars, and black holes. White dwarfs are fascinating objects. They are the exposed cores of dead stars, packed with the density of diamonds. Initially, they are extremely hot, glowing with a fierce bluish-white light. But they have no internal power source. They are like stones taken out of a fire. They only glow because they are still holding on to the heat of their past lives. For a time, the universe will be lit by this corpse light. It will be a ghostly, pale illumination, incredibly faint compared to the brilliance of living stars. The color of the universe will shift from the maroon of the red dwarfs to a faint spectral gray-blue, the color of cooling ash. But this phase is merely a transition to total darkness. A white dwarf loses its heat into the vacuum of space. It cools from blue to white to yellow to red. Eventually, after quadrillions of years, The white dwarfs will cool so much that they stop emitting visible light entirely. They will become black dwarfs, cold, dark, crystal spheres drifting through the void. They will be invisible to any eye, detectable only by their gravity. At this point, the universe will be truly black. The dark night sky that we perceive today as an illusion will finally become the reality. However, there is one last source of light, though it is one that challenges our very definition of the word: black holes. As the stellar remnants cool and fade, the supermassive black holes at the centers of galaxies will continue to grow, swallowing the dark matter and the dead stars that wander too close. For a long time, the accretion disks around these black holes, the swirling drains of matter falling in, will provide the only significant light in the universe. These disks glow with X-rays and ultraviolet radiation, casting harsh, invisible beams into the dark. But even the black holes are not immortal. As the physicist Stephen Hawking theorized, black holes emit a faint form of radiation, now known as Hawking radiation. They slowly evaporate over timescales that defy notation, years numbering in the Googles. As they evaporate, they glow. In their final moments, before they disappear completely, a black hole will explode with a burst of gamma rays. In the profound darkness of the far future, these rare, fleeting flashes will be the only events breaking the monotony of the void. And we must not forget the expansion. While the stars are dying and the lights are fading, the space between the galaxies is stretching faster and faster. This big freeze scenario means that eventually the galaxies will be pulled away from one another at speeds exceeding the speed of light. To an observer in the far future, the universe will appear to be empty. The light from other galaxies will never reach them. The cosmic microwave background, that ghost of the Archaea, orange fireball, will be stretched until its wavelength is larger than the size of the observable universe itself. It will become physically undetectable. The color of the universe in this final state is a concept that loses its meaning. Color requires a contrast. It requires a photon to strike an eye. In the heat death of the universe, the photons will be stretched to essentially zero energy. The temperature of the cosmos will approach absolute zero. The universe will be a sea of maximum entropy, a place where nothing happens, nothing changes, and nothing shines. It will be the ultimate, eternal black. This trajectory, from the primordial orange to the blue youth, to the beige present, to the red age, and finally to the eternal black, places our current existence in a startling context. We often take the beauty of the night sky for granted. We assume that the stars are a permanent fixture of reality, that the universe is designed to be a place of light and color. But the scientific story tells us otherwise. The era of light is an anomaly. It is a brief, transient phase in the life of the cosmos. The universe spent its first few 100 million years in the dark, and it will spend the vast, infinite majority of its future in the dark. We are living in the flashbulb moment. We have opened our eyes during the single, short interval where the universe is blazing with activity, where the chemical balance allows for biology, and where the light is bright enough to see across the cosmos. The cosmic latte, that humble shade of beige, is therefore something precious. It is the color of life. It is the color of a universe that is hospitable. The fact that we are here to see it, to measure it, and to name it is a stroke of immense cosmic luck. We are the witnesses. We are the universe's way of seeing its own colors before they fade away forever. Paradoxically, knowing the end of the story resolves the mystery we started with. We began by asking why the sky is dark at night. We learned that it is dark because the universe is young and expanding. But if we could wait long enough, the sky would be dark for a different reason, because the universe is dead. The darkness we see between the stars is not a void. It is a window into the future. It is a preview of the state that awaits all things, but for now, the stars are still burning. The hydrogen is still fusing. The great galaxy in Andromeda is still spiraling in the dark, brilliant with blue clusters. The nebula of Orion are still glowing with the fierce teal of oxygen and the deep red of hydrogen. The universe is still painting with light.